All right, so this question here is from 2004. It's question number 3 on the 2004 FRQ. So we have this loop. We have the dimensions of the loop. So the area is going to be 0.04 meters squared. Just multiply those two sides together. What else do we have? This magnetic field is 0.03 Tesla. And then we're given the resistance of the loop as 0.6 ohms. All right, first question, calculate the magnetic flux through the loop. So I'll do that down here. So A, the equation for magnetic flux is BA cosine theta. So our magnetic field is 0.03 Tesla. The area of the loop is 0.04 meter squared. And then cosine, what's the theta here? 0. Cosine of 0. Why is it 0? The theta is the angle between the normal line to the loop and the field. So, look, here's a loop. The normal line is sticking straight out, right? Normal means perpendicular. The field is going straight in. What's the angle between those? 0. They're parallel to each other. All right, so cosine of 0 is just 1, so we can pretty much just drop this off. We don't need it. Cosine of 0 is 1. So this calculation comes out as now look at units, 0.0012 Tesla meter squared. A Tesla meter squared is equivalent to the Weber, WB. But if you put Tesla meter squared, that's fine. It's equivalent, okay? All right, second question. So now what they say is this. The field strength now increases to 0.2. So this is what we got. Our initial magnetic field is 0.03, and our final magnetic field is 0.2. All right, the key idea for this whole topic of induction is simply this. When magnetic flux changes, so here's our equation for magnetic flux. When magnetic flux changes, we get induced voltage. Now in this problem, what's causing the flux to change? Is it B, is it A, or is it theta? Which one's changing? B. So what we can do, so the equation for induction is this. Induced voltage is N, change of flux over time. Our N is 1, right? N is number of loops. There's one loop here, so that just goes to 1. Now what can we say about change of flux, right? So here's our flux equation. Change of flux would be delta B times A, wouldn't it? That's how you would calculate your change of flux. Okay, don't worry about the cosine theta because that's just 1. All right, over delta T. All right, what's the delta B here? What's the change of flux? Well, let's see. 0.03 to 0.2, what's the change? 0.17. The area is constant at 0.04, and then the time is given right here. 0.5 seconds. All right, so this gives us an induced voltage of 0.0136. That's the induced voltage. Now, part C. So we're right here. Calculate the magnitude of the current in the loop. So to figure out the current in the loop, we're going to just use Ohm's law. So I'm going to erase this over. So to figure out the current, E equals IR. Same thing as delta V equals IR. I think everybody knows this at this point. E is EMF, which is another name for voltage. So I is going to be our induced voltage over the resistance, 0.0136 volts, divided by the resistance, which is given right here, 0.6 ohms. So we get an induced current of 0.0227 amps. All right, and then what is the direction of the current in the loop? Okay, to figure out the direction of the current, you got to use Lenz's law. Lenz's law says the induced current will create a magnetic field opposite the change of flux. So for this problem here, we go from a magnetic field of 0.03 in to a magnetic field of 0.2 in. Which way did the flux change in this loop? Did the flux change in or did it change out? We went from a magnetic field in to a stronger magnetic field in. That's a change in what direction? In. So the induced current will create a magnetic field, a separate magnetic field. We're not talking about this magnetic field, a separate magnetic field out. So you got to do right hand rule number 2. You put your hand around that loop, your forefingers curling out, and your thumb points counterclockwise. So the direction of the current is counterclockwise. And then what do you say when you justify your answer? You could say, what would be a good thing? Justify answer, you could say induced current creates a B field opposite the change of flux. Something like that. And the change of flux was in, so the induced current creates a magnetic field out. All right, last question here. Describe a method by which you could induce a current if the magnetic field remained constant. So now, what happened in this problem is the magnetic field changed. But what's another way we could have induced current besides messing with the B field? What else could we have done? Well, let's look at the flux equation. The flux equation is B, A, cosine theta. So instead of messing with B, like let's leave B alone, B stays constant. What else could you have done? You could have done what? Change the area of the loop, like maybe pull it from the corners, like grab the corners and go bang, pull it so it closes, Or you could have messed with theta. That would be like this. Like here's your loop. Instead of the magnetic field going in, so the problem starts like this with the magnetic field going in. Well, what if you turned the loop like that? Would there be a flux anymore? Because the field couldn't get inside the loop. So you could either talk about changing the area of the loop or rotating the loop.